One of the most profound and often misunderstood truths in physics is that every force in the universe comes in pairs. This principle, known as Newton's third law of motion, is summarized in one of the most iconic scientific statements ever written. For every action, there is an equal and opposite reaction. Although it sounds simple, this idea reveals a deep and elegant structure behind how motion actually works. It explains why rockets rise, why birds can fly, why walking is possible, why cars move forward, and even why planets remain in motion. To understand the true nature of these force pairs is to see how movement is transferred from one object to another, forming an unbroken chain of interactions that shape the entire physical world. At its core, the concept means that whenever one object exerts a force on another, the second object simultaneously exerts a force of equal strength, but in the opposite direction on the first. These forces do not cancel each other out because they act on different objects. Instead, they create interactions that determine how the two objects respond, accelerate, or remain stable. This is what makes motion possible. Force pairs transfer energy, momentum, and pressure between objects in predictable ways. Consider something as simple as jumping off the ground. When you crouch and push downward with your legs, you exert a force on the earth. According to Newton's law, the earth responds instantly by pushing upward on you with an equal force. That upward reaction force is what propels your body into the air. Even though Earth is unimaginably massive compared to your body, the same sized force it experiences from you produces almost no observable motion in the planet itself. You rise dramatically, but Earth's acceleration is so tiny it cannot be detected. Yet the interaction still occurs. You push on the Earth, and the Earth pushes on you. This same principle explains why walking works. Most people assume that when we move forward, it is because we push our bodies ahead using leg muscles. But that is only half the truth. The real mechanism is the friction between your foot and the ground. When you push your foot backward against the ground pushes your foot forward with an equal and opposite force. That forward reaction from the ground is what actually moves your body. Without friction, and therefore without an equal and opposite force, you would simply slide in place, unable to take even one step. This is why running on ice or a smooth floor is difficult. The lack of friction weakens the reaction force needed to propel you forward. Action-reaction pairs also explain why cars accelerate. When the wheels turn, they push backward on the road. The road, in turn, pushes the wheels forward. This forward reaction is what makes the car move. Again, it may feel like the engine is pushing the car itself, but in reality, motion comes from the road pushing back. The transfer of force is hidden in the interaction between tire and ground. Without that backward push from the tires, no forward reaction would exist. This is the reason why cars get stuck in mud or snow. The tires cannot push effectively on the surface, so the reaction force cannot push the car forward. The principle extends to more complex systems as well, such as flight. When a bird flaps its wings downward, it pushes air molecules down with tremendous speed and pressure. In response, the air pushes the bird upward with an equal and opposite force. That upward reaction is lift. Airplanes operate by the same rule. Their wings deflect air downward, and the air responds by pushing upward, holding the plane in the sky. In both cases, motion transfers from wing to air and back again, creating a mutual interaction that allows sustained flight. Without these pairs of forces, no creature and no aircraft could rise from the ground. The same mechanism explains the soaring power of rockets. Unlike cars or birds, Rockets cannot rely on ground or air surfaces for pushback. Instead, they create their own medium for reaction. When a rocket burns fuel, it expels hot gas downward at extremely high velocity. The rocket pushes the gas downward, and the gas pushes the rocket upward. These two forces exist as a pair. Importantly, this reaction does not depend on the presence of air, which is why rockets work in the vacuum of space. The motion of one substance, exhaust gases, transfers momentum back to the rocket, producing upward movement. This idea of transfer of motion is crucial. When forces come in pairs, motion is not created from nowhere. It is passed from one object to another, obeying the deeper law of conservation of momentum. When you throw a ball forward, your hand exerts a force on the ball, and the ball exerts an equal and opposite force on your hand. The ball moves forward because you give it momentum, but you also feel your hand move slightly backward or your body shift due to the reaction force. This is the reason why firing a gun causes recoil. The bullet is pushed forward, and the gun is pushed backward with an equal force. The motion of the bullet is balanced by the motion transferred to the gun and your body. Even interactions that seem effortless rely on this law. When a swimmer moves through water, they push the water backward with their hands and feet. The water pushes them forward. When a fish swishes its tail, it pushes water behind it. The water pushes the fish in the opposite direction. Consider sitting in a chair right now. You are pushing down on the chair with your weight, and the chair pushes upward on you with an equal amount of force, allowing you to remain seated without sinking through it. These examples show that motion is not just an individual property. It is the result of interactions between objects. Every movement is the result of forces being exchanged, balanced, or transferred. There is no isolated push or pull. Every force in the universe is part of a pair, mirroring and opposing its partner. This dual nature ensures that momentum within a system remains conserved and interactions remain consistent. Understanding this reveals a deeper truth about the physical world. No object acts alone. Everything that moves or changes does so because it is part of a connected network of forces. Whether it is a rocket lifting into space, a dancer pushing off the floor, a bird soaring through the air, or a simple step taken on a sidewalk, the same fundamental rule holds. Forces always come in pairs, and it is through these pairs that motion is transferred, energy is exchanged, and the dynamic world around us continues to function with astonishing precision. Sir Isaac Newton's discoveries did far more than reshape scientific theory. They built the foundation upon which modern engineering, space exploration, and advanced technology stand. Before Newton, humankind understood motion, force, and gravity only in fragments. People could observe how things moved, but they did not understand why they moved. Engineers could build structures, but they lacked the precise mathematical tools to predict stresses, forces, and failures. The idea of sending machines or humans beyond Earth was unimaginable because the principles governing planetary motion and gravity were not yet understood. Newton changed all of this. His laws of motion, calculus, and universal law of gravitation created a blueprint for the technological age. Newton's first major contribution to engineering and technology was his three laws of motion. These laws provided the world with a predictable and universal way to understand how objects behave under different forces. Engineers could finally calculate how much force was required to move an object, slow it down, lift it, or keep it stable. Before Newton, builders relied heavily on trial and error. Bridges, ships, and buildings were made based on experience and intuition. After Newton, design became scientific. Engineers gained the ability to analyze forces mathematically, predict failures before they occurred, and optimize structures for strength, efficiency, and stability. For example, Newton's second law of motion, force equals mass times acceleration, became the cornerstone of mechanical engineering. It allows precise prediction of how machines will behave under different loads. Whether designing a car engine, a crane, or a high-speed elevator, engineers depend on Newton's framework. Every vehicle braking system, every aircraft landing, every industrial robot arm, and every roller coaster relies on calculations derived from Newtonian principles. These laws empowered humanity to build larger bridges, safer buildings, stronger machines, and more reliable transportation systems. Another monumental contribution was Newton's development of calculus. Although his laws of motion describe how objects behave, calculus gives engineers the mathematical language needed to apply those laws in complex, real-world situations. Almost every branch of modern engineering, civil, mechanical, aerospace, chemical, electrical, depends on calculus. Calculus allows engineers to compute stress on bridges, determine fluid flow through pipelines, optimize aerodynamic shapes, and design electrical circuits. Without Newtonian calculus, the precision and scale of modern engineering would be impossible. Newton's insights did not just strengthen engineering, they opened the door to space travel itself. Newton was the first to understand that gravity is not limited to Earth. His law of universal gravitation revealed that the same force causing an apple to fall also governs the orbits of the Moon, planets, and comets. This was an astonishing revelation. It unified the heavens and the earth under one law. Suddenly, planetary motion could be calculated with mathematical precision. Space travel depends entirely on Newton's ideas. Rocket scientists use Newton's laws to calculate thrust, acceleration, and trajectory. The third law for every action, there is an equal and opposite reaction, is the fundamental principle behind rockets. When a rocket expels gas downward, the reaction force pushes the rocket upward. Without this Newtonian truth, there would be no propulsion in space. The concept of orbital motion is also rooted in Newton's thinking. He famously imagined a cannon on a high mountain firing a projectile so fast that it would fall toward Earth indefinitely without ever hitting the ground, essentially describing an artificial satellite centuries before satellites existed. Today, satellites orbit Earth exactly the way Newton predicted. Engineers calculate launch velocities, orbital decay, escape velocity, and interplanetary travel using formulas directly derived from Newton's gravitational law. Modern space missions, whether launching GPS satellites, sending rovers to Mars, or guiding astronauts to the International Space Station, are impossible without Newton's equations. Even advanced missions that involve slingshot maneuvers around planets rely on understanding how gravity pulls on objects in motion. Every spacecraft trajectory is a precise dance choreographed using Newton's physics. Beyond engineering and space travel, Newton's insights shaped modern technology in countless ways. Nearly every technological system involves forces, motion, energy transfer, or acceleration, all concepts rooted in Newton's work. For instance, robotics relies on Newtonian mechanics to calculate torque, force, and movement. Autonomous vehicles use Newton-based algorithms to understand how braking or acceleration affects trajectory and stability. Computer simulations, animations, and physics engines in video games are built on Newton's laws to create realistic movement. Even technologies that seem unrelated to physics, such as smartphones, rely indirectly on Newton's discoveries. The accelerometers inside phones measure acceleration using principles derived from Newton's second law. GPS systems use satellites that orbit Earth according to Newton's gravitational equations. Medical imaging devices, such as CT scanners, use rotating equipment designed based on Newtonian mechanics to produce stable and precise images. Newton's laws also shaped structural engineering, allowing architects to build skyscrapers that withstand wind forces, earthquakes, and vibration. Engineers use Newtonian models to analyze how forces distribute through beams and columns, ensuring buildings remain stable under pressure. This understanding allowed the construction of bridges stretching miles, massive dams holding back billions of gallons of water, and safe transportation systems carrying millions of passengers daily. In the industrial world, Newton's insights enabled the creation of engines, turbines, pumps, and manufacturing machinery. Every rotating wheel, conveyor belt, robotic system, and hydraulic press depends on Newtonian mechanics. Factories today are filled with devices that rely on precise control of force, speed, and acceleration, all predicted by Newton's formulas. Even modern energy systems trace their origins to Newton's work. Wind turbines rotate because the air pushes their blades. Newton's laws describe the motion, torque, and power output. Hydroelectric turbines use flowing water to generate electricity. Again, Newtonian principles explain how pressure and momentum translate into rotational force. It becomes clear that Newton's insights were not just scientific milestones, they were technological seeds. From his laws grew the engines that drove the Industrial Revolution. From his calculus came the mathematical tools that built the modern world. From his universal law of gravitation came the roadmap for exploring the cosmos. What makes Newton's contributions truly remarkable is their universality. His laws apply to falling apples and orbiting planets, to racing cars and rising rockets, to smartphones and skyscrapers. Every breakthrough in engineering, every advance in space travel, and every modern technological marvel can trace its origins back to the truths Newton uncovered. His work stitched together the fabric of motion, force, and gravity in a way that continues to guide human innovation centuries later. Physics is often described as the study of how the universe behaves, but for most people, its rules remain invisible. We see objects fall, cars move, and planets orbit, yet we rarely pause to question the unseen principles behind these motions. Newton's laws of motion and his law of gravitation serve as the key that unlocks this hidden world. When we understand these laws, the ordinary becomes extraordinary. Simple everyday actions transform into complex interactions governed by clear, logical patterns. Newton's insights peel back the surface of reality and reveal the invisible machinery that makes everything work. At their core, Newton's laws show us that motion is not random or mysterious. It is governed by predictable rules. Every step we take, every object we lift, every vehicle we ride in follows these laws with perfect consistency. Without knowing this deeper truth, we only witness the surface-level behavior of objects. But once we learn these principles, we begin to see an entire network of forces guiding the world around us. Consider something as basic as a cup sitting on a table. Before understanding physics, we simply accept that the cup stays still. But Newton's laws transform that stillness into a layered explanation. The cup remains at rest because of inertia. It resists any change in its motion. Gravity pulls it downward, but the table pushes upward with equal force, creating a balanced state. These forces act continuously, quietly maintaining equilibrium. The cup isn't just sitting there. It is participating in a constant interaction of forces that keeps it stable. What seemed simple becomes remarkable. Walking is another everyday action that takes on new meaning through Newton's laws. It seems natural to assume that our legs push us forward, but physics reveals a more fascinating truth. When our foot pushes backward on the ground pushes forward on us. That forward reaction force is what propels us ahead. Without friction to create that opposing force, we would simply slide. Understanding this reveals the hidden partnership between our bodies and the earth, a dance of forces that makes movement possible. These laws don't only describe human activities, they explain natural phenomena as well. When a leaf falls from a tree, gravity accelerates it downward. Air resistance pushes upward, slowing its descent. The leaf flips and tumbles because differing forces act on its uneven shape. What seems like a gentle drift is actually a complex physics event involving multiple forces interacting simultaneously. Newton's laws act like a spotlight, illuminating these invisible interactions. A rolling ball provides another example of hidden physics at work. A child may think the ball stops because it becomes tired, but Newton's first law tells us the ball would roll forever unless a force, like friction, interferes. This law uncovers the truth that motion does not fade away on its own. It is interrupted by forces acting on the object. Understanding this changes the way we see movement. It becomes a dialogue between objects and the environment. The invisible physics shaping our world becomes even more astonishing when we look at large-scale phenomena. The tides, for instance, are not merely the ocean moving in and out. Newton's law of gravitation reveals they are caused by the moon's gravitational pull, which stretches Earth's oceans. Even though the moon is far away, its force influences vast bodies of water, raising and lowering sea levels daily. Understanding this transforms the simple act of watching waves into observing a celestial interaction between Earth and the moon. Similarly, the stability of buildings and bridges becomes a marvel through Newton's laws. Engineers design structures by calculating how forces like gravity, wind, and load will act on them. A skyscraper standing firm in strong winds is not a coincidence. It is the result of carefully predicting how forces will flow through beams and foundations. Newton's laws are embedded in steel frames, concrete structures, and suspension cables, ensuring that buildings can withstand the unseen forces of nature. Transportation is another domain shaped entirely by Newtonian physics. Cars rely on force, acceleration, and friction. Airplanes lift because their wings cause air to push upward. Trains glide because momentum and low friction allow smooth movement. Even bicycles depend on balanced forces to remain upright. Once we understand the physics behind these machines, they become more than inventions. They become applications of universal laws we now recognize. Perhaps the most awe-inspiring example of hidden physics is found in space. Planets orbit the sun because the gravitational force between them creates a balance between their forward motion and the sun's pull. Satellites stay in orbit for the same reason. Comets travel on long, looping paths dictated by gravitational interactions predicted centuries ago by Newton. Understanding this makes the night sky feel alive with motion governed by laws we can calculate and understand. The universe becomes less mysterious and more elegantly structured. Even technology in our hands every day functions because of Newton's principles. The accelerometer in a smartphone measures changes in motion using Newton's second law. Virtual reality systems track movement using physics-based algorithms. Robots move with precision because engineers apply Newton's equations to calculate force, torque, and acceleration. Without understanding these laws, these technologies would seem magical. With understanding, we see the physics powering their operation. This hidden physics also shapes natural disasters. Earthquakes involve rapid shifts in tectonic plates, releasing energy that moves through Earth's crust. Newton's laws describe the resulting acceleration of the ground and the forces buildings experience. Understanding these forces allows engineers to design structures that can withstand earthquakes. Hurricanes, tornadoes, and floods are influenced by pressure changes, fluid dynamics, and gravitational forces. Physics explains why they grow, move, and dissipate. Seeing these events through Newton's laws makes their behavior less unpredictable and more understandable. Ultimately, understanding Newton's laws is like gaining access to a secret layer of reality. Everyday motion becomes a series of elegant, predictable interactions. Natural phenomena become understandable rather than mysterious. Technology becomes an expression of mathematical truths rather than mechanical magic. The world becomes a vast stage where every object moves according to rules we can decode. These laws reveal that the universe is not chaotic. It is structured, ordered, and governed by fundamental principles. They expose the hidden architecture of motion, force, and gravity that shapes everything from the smallest pebble on a path to the most distant planet circling a star. Once we grasp these laws, we no longer simply live in the world. We understand it. And that understanding transforms the ordinary into the extraordinary, showing us that the physics behind our everyday lives is far more beautiful, complex, and powerful than we ever imagined. Gravity, not a pulling force, but the natural attraction of mass gravity, is one of the most familiar forces in our everyday experience. We feel it every moment as it anchors us to the ground, keeps objects from floating away, and controls the motion of planets, moons, and stars. Yet, despite its familiarity, gravity is deeply misunderstood. One of the most striking truths is that gravity is not a pulling force in the way many imagine. Instead, gravity is a natural consequence of mass attracting mass, mutual interaction between objects simply because they possess mass. This idea originates from Isaac Newton's revolutionary thinking. Before Newton, people could describe what gravity did. Objects fell downward, the moon orbited the Earth, but they could not explain why. Newton was the first to recognize that gravity is not a mysterious downward force limited to Earth. It is a universal phenomenon. Every object with mass attracts every other object with mass. This means the Earth pulls on the moon pulls on the Earth, your body pulls on the chair beneath you, and even 2 grains of sand pull on each other. These forces are usually too small to notice, but they are always present. When Newton described gravity as mass attracting mass, he presented a radically simple and powerful idea. He was not claiming that the Earth sends out invisible ropes or strings that hook objects and pull them in. Instead, he proposed that every object naturally exerts a force on other objects in proportion to their mass. In essence, gravity is a mutual attraction, like a silent handshake between masses. The more massive an object is, the stronger its gravitational influence. This is why planets, stars, and galaxies dominate motion on cosmic scales, while smaller objects like apples, tables, or even cars have tiny gravitational effects. The power of this concept becomes clear when we examine everyday situations. When you drop a ball, the Earth does not reach upward and physically grab it. Rather, the ball and Earth exert gravitational attraction on each other. Because the Earth's mass is enormous compared to the ball's, it appears that only the ball moves. In reality, the Earth moves too, but by an amount so small it is practically unmeasurable. This idea also explains why astronauts on the International Space Station appear weightless. They are not free from gravity. In fact, Earth's gravity at their altitude is nearly as strong as at the surface. They are weightless because they are in continuous freef, all around the Earth, mutually attracting each other in a constant orbital dance. However, Newton's explanation of mass attracting mass was only the beginning. Centuries later, Albert Einstein expanded our understanding with his theory of general relativity. Einstein described gravity not as a force but as a curvature, or bending, of space and time caused by mass. According to Einstein, massive objects distort the space around them, and other objects move along the curves created by this distortion. In simple terms, mass shapes the stage on which motion occurs. But even in Einstein's deeper framework, the idea remains consistent with Newton's statement. Gravity emerges because masses interact. The attraction is not a physical pull, but the natural result of how mass influences the environment around it. This theory helps explain puzzling behaviors that Newton's laws could not, such as the precise orbit of Mercury or the bending of starlight around the Sun. Yet the essence remains grounded in the idea that mass does not pull. It merely causes objects to move toward one another due to their natural interaction. Returning to Newton's perspective, we can appreciate how mass attracting mass explains countless daily observations. Consider why you stay firmly planted on the Earth. Your body has mass, and the Earth has mass. Their mutual attraction keeps you grounded. You might wonder why you don't see the Earth move toward you. Again, it does, but only by a microscopic amount because the Earth's mass is so much greater than yours. Similarly, when you throw a ball upward, gravity does not pull it back like a magnet. Instead, the ball's mass and Earth's mass attract each other. The upward motion eventually slows because the force of attraction between the two remains constant until the ball reverses direction. If gravity were a true pulling force, it would raise many unanswered questions. What would do the pulling? How would the force reach across empty space? Newton avoided these complications by describing gravity as a natural property of mass. He famously stated that he did not claim to know the mechanism behind gravity, only that it existed and behaved in mathematically predictable ways. His humility reflected the depth of the mystery, but his equations forever changed the way we understand motion. The concept of mass attracting mass clarifies phenomena on massive cosmic scales as well. Planets orbit the Sun not because the Sun pulls them by strings, but because its massive presence creates a strong mutual attraction that guides their motion. Galaxies form because clouds of gas and dust attract each other, gradually condensing into stars and planetary systems. Black holes exert such intense gravitational attraction that not even light can escape. Even planets affect each other. Jupiter, for example, influences the orbit of Mars and helps stabilize the asteroid belt. Understanding gravity in this way also reveals why everything in the universe is connected. If every mass attracts every other mass, then every star influences every planet influences every moon, and even objects separated by billions of kilometers exert some gravitational sway. Though these effects may be inconceivably small, they demonstrate the deep interconnectivity of the universe. Gravity binds everything together in a shared web of motion. The idea that gravity is simply the result of mutual attraction rather than a pulling force also has practical applications. Engineers designing bridges and skyscrapers must consider gravitational attraction between structures and the Earth. Rocket scientists must account for gravitational forces when launching spacecraft, calculating how much thrust is needed to overcome Earth's attraction. Astronomers predicting planetary movement rely entirely on calculations rooted in mass-based attraction. Ultimately, the statement gravity is not a pulling force, but the result of mass attracting mass, is more than a scientific fact. It is a window into a deeper truth about the universe. Gravity is not an external force acting upon objects, but an inherent relationship between them. Everything with mass participates in this relationship. It is not a force imposed from outside, but a natural interaction embedded in the fabric of reality. When we understand gravity this way, the world becomes richer and more profound. Every falling object, every orbiting moon, every step we take is part of a universal pattern of attraction that links all masses together. We are not simply held to the Earth, we are connected to it, and the Earth, in turn, is connected to the rest of the cosmos. Gravity is the silent architect, shaping everything from the smallest grain of sand to the largest galaxies, not by pulling, but by the inherent attraction of mass to mass. Inertia, the hidden force of stillness and motion, inertia is one of the most fundamental and fascinating principles in physics, yet it is also one of the most overlooked. We witness it constantly. When a car suddenly stops and our bodies jerk forward, when a ball keeps rolling until friction slows it, when a book remains motionless on a table until someone moves it. These everyday experiences reflect a deeper truth. Objects naturally resist any change in their current state of motion, whether they are standing still or moving. This property is what scientists call inertia, and it lies at the core of Newton's first law of motion. Newton's first law tells us that an object at rest will remain at rest, and an object in motion will continue moving in a straight line at a constant speed, unless an external force acts on it. This principle reveals that motion or stillness is not something objects choose or work to maintain. Instead, inertia is an inherent characteristic of matter itself. Every object, whether a tiny grain of sand or a massive planet, possesses inertia simply because it has mass. To understand inertia more clearly, imagine a heavy boulder lying on the ground. It will not begin to move on its own. Even if you push it gently, the boulder barely shifts because its inertia resists your attempt to change its state. A much stronger force is needed to overcome that resistance. On the other hand, once the boulder is rolling, it will not stop immediately. Now its inertia resists your attempt to bring it to rest. This dual nature, resisting both starting and stopping, is what makes inertia such a powerful and universal principle. Inertia is closely linked to mass. The greater an object's mass, the greater its inertia, and the more force is required to change its motion. This explains why lifting a small box is easier than lifting a large one, or why pushing a heavy car requires much more effort than pushing a bicycle. The objects with more mass have more inertia and therefore put up more resistance to being moved or stopped. This relationship between mass and inertia is central to our understanding of motion and is the reason engineers, athletes, drivers, and scientists must constantly consider how inertia influences the behavior of objects. One of the clearest examples of inertia occurs in vehicles. When a car is moving at high speed, both the car and the passengers inside are also moving at that speed. If the driver brakes suddenly, the car slows down, but the bodies inside want to keep moving in the same direction and speed due to inertia. This is why you lurch forward unless restrained by a seatbelt. The seatbelt applies an external force that counters your inertia, preventing you from continuing forward. Without seatbelts, inertia would cause passengers to collide with the interior of the car at dangerous velocities, sending them forward even though the vehicle has stopped. This simple yet life-saving concept shows how inertia is not just a scientific idea. It directly affects safety and survival. Another powerful demonstration of inertia can be seen in sports. A soccer ball lying on the ground remains motionless until a player kicks it. The kick provides the external force that overcomes its inertia. After being kicked, the ball continues moving across the field until friction with the grass, air resistance, or another player's foot slows it down. The ball's tendency to keep moving is its inertia at work. When a baseball is struck with a bat, the force of the bat must overcome the inertia of the resting ball. The stronger the force, the greater the change in motion. Athletes train specifically to apply force efficiently because overcoming inertia quickly is often the key to strong performance. Inertia is not limited to physical objects like cars and balls. It also applies to the natural world on a cosmic scale. Planets orbiting the Sun provide a breathtaking example. If there were no external forces, a planet would continue moving in a straight line through space forever. But the gravitational pull of the Sun counteracts this inertia, constantly bending the planet's path into an orbit. Inertia tries to keep the planet moving straight. Gravity tries to pull it inward. The balance between inertia and gravity results in stable, predictable orbits. Without inertia, the planets would immediately fall into the Sun. Without gravity, they would shoot off into space. The harmony of these forces shapes the entire structure of our solar system. Even astronauts floating in space experience inertia in a dramatic way. Once they push off a surface, their bodies drift smoothly in a straight line until they hit something. There is almost no air resistance or friction in space to slow them down, so inertia becomes even more obvious. The lack of external forces makes their constant motion a perfect demonstration of Newton's first law. This behavior highlights the universality of inertia. It does not depend on location, environment, or object type. Whether on Earth or in space, in motion or at rest, inertia governs the behavior of matter everywhere. Inertia also plays a significant role in our daily interactions with machines and tools. When we operate a lawnmower, vacuum cleaner, or power drill, we feel resistance when starting or stopping the device. That resistance is inertia. A shopping cart filled with groceries is harder to push because its greater mass increases its inertia. Even household chores like moving furniture, sweeping, or lifting boxes involve battles with inertia. We constantly apply forces to overcome the natural resistance objects have to changes in motion. Inertia affects not only objects, but also energy systems. For example, flywheels and engines rely on inertia to store rotational energy. Once spinning, the flywheel continues rotating with little added force because its inertia keeps it moving. This property stabilizes the engine's performance and ensures smoother operation. In manufacturing, heavy industrial machines such as presses and rollers use inertia to apply consistent force to materials. Without inertia, these systems would be unstable and inefficient. Understanding inertia also reveals deeper insights about human motion. When you start running, your body resists the initial push, requiring effort to accelerate. Once you reach a steady pace, maintaining motion becomes easier because your inertia keeps you moving. When you suddenly stop, your body wants to continue forward, and your muscles must apply force to counter your own inertia. Every movement you make, walking, throwing, bending, dancing, is influenced by your body's mass and its resistance to changes in motion. Ultimately, inertia is not just a physical concept, it is a universal truth about matter. It governs how planets move, how athletes perform, how machines operate, and how we navigate the world. Understanding inertia gives us a clearer picture of why objects behave the way they do and how forces interact with matter. It explains why motion is not easily changed and why stillness is not easily broken. Objects do not resist change because of any internal intention or energy, but because inertia is built into the very structure of mass itself. In simple terms, inertia is nature's way of saying that every object prefers to keep doing what it is already doing, whether that is resting quietly or racing through space at tremendous speed. This principle is one of the pillars of classical physics and a cornerstone of our understanding of the universe. When we say that Newton revealed the universe operates on predictable, mathematical laws instead of mystical or arbitrary forces, we are describing one of the greatest intellectual revolutions in human history. Before Newton, natural events were interpreted through a mixture of superstition, philosophy, religious explanation, and fragmented scientific ideas. People observed patterns in nature, but did not understand why they occurred. Storms, tides, eclipses, planetary motion, falling objects, and the behavior of machines were explained through beliefs rather than through tested principles. Newton shattered that world by showing that the universe behaves according to consistent rules that can be expressed through mathematics. This shift represented the birth of modern science. To appreciate the magnitude of Newton's revelation, we must visualize the world before his time. For thousands of years, natural explanations depended heavily on mythology and divine intervention. Civilizations from the Babylonians to the Greeks linked celestial events to deities. Comets were considered omens sent by gods. Eclipses were believed to be supernatural warnings. Even earthquakes and storms were interpreted as expressions of divine anger or otherworldly forces. People lived in a universe that felt unpredictable, governed by whims and mysteries that could not be questioned. The idea that nature followed rigid, measurable laws was not part of human understanding. Philosophers like Aristotle proposed explanations based on observation, but these explanations were qualitative, not quantitative. Aristotle claimed heavier objects fall faster than lighter ones, not because he measured it, but because it seemed logical. He believed heavenly bodies moved in perfect circles because circular motion was pure, not because he had evidence. These ideas became deeply embedded in human thought, persisting for centuries because no one provided a better framework. Even when scientists like Galileo challenged these views, their insights were not fully unified into a single system. The world still lacked a comprehensive, mathematical explanation of how nature works. This intellectual vacuum created uncertainty. Humans lived in a universe they could observe but not understand. Motion was poorly explained. Gravity was seen as a strange tendency of objects to fall downward, not as a universal force. Planetary motion was described using complicated geometric models that could predict positions but offered no explanation for why celestial bodies moved the way they did. There was science, but it was limited descriptive rather than explanatory. Observations were collected without being connected to deeper principles. Ideas were debated without rigorous mathematical foundations. Then Newton appeared, and the entire landscape of knowledge shifted. Newton recognized that nature could be understood through mathematics, and that these mathematical principles were universal. He proposed that motion, force, and gravity were not arbitrary behaviors, but governed by precise laws that apply everywhere. This was a shocking idea at the time. Newton's insight meant the same equations that describe a falling apple also describe the orbit of the moon. This unification of earthly and celestial physics was unprecedented. For the first time, humans understood that the universe is not divided into mysterious realms, but operates under the same consistent rules from top to bottom. Newton demonstrated that these rules could be expressed in mathematics, the most precise language humans possess. His laws of motion and his universal law of gravitation were not metaphors or philosophical statements, but literal equations. This mathematical precision was revolutionary. Instead of vague ideas about motion, Newton offered formulas that could predict future behavior with astonishing accuracy. Instead of assuming nature behaved according to its own mysterious will, Newton showed that it behaves according to measurable quantities like mass, distance, velocity, and force. This shift replaced guesswork with calculation, superstition with certainty, and mystery with clarity. The most profound aspect of Newton's revelation was predictability. Before him, the universe felt unpredictable because no one understood the forces behind natural events. Newton showed that once you know the conditions of a system, you can calculate its future. Given an object's mass and the forces acting upon it, you can predict how it will move. Given the positions and masses of planets, you can predict their orbits centuries into the future. This predictability was power. It meant that nature could be understood, controlled, and harnessed. It meant humanity could move from simply observing nature to mastering it. Newton's discovery that the universe follows mathematical laws also created a new world, view in which physical phenomena are interconnected. Prior to him, different phenomena were treated as isolated mysteries. Gravity explained falling objects, but had nothing to do with tides or planets. Motion in the heavens was seen as different from motion on Earth. Newton unified these separate realms under one principle, universal gravitation. This unification showed that everything in nature is part of a coherent system. The same gravitational force that pulls a stone downward also shapes orbits, controls tides, and influences the paths of comets. This was a monumental intellectual leap, revealing a universe governed not by chaos, but by elegant mathematical relationships. What made Newton's revelation so powerful is that it was testable. Unlike mystical explanations, Newton's laws produced predictions that could be verified through measurement and experiment. Scientists tested his equations and found them accurate again and again. Ships could navigate using Newtonian physics. Engineers could design machines with predictable outcomes. Astronomers could calculate planetary positions with unparalleled precision. The accuracy of Newton's predictions validated the idea that nature truly is governed by mathematical laws, not arbitrary events. This confirmation created a foundation for scientific confidence that persists to this day. This shift from mystical to mathematical thinking marked the beginning of the scientific age. Newton showed that to understand the world, one must measure it, quantify it, and express its behavior in mathematical form. This approach led to a rapid expansion of scientific discovery. Researchers began applying mathematical reasoning to other fields: optics, fluid dynamics, thermodynamics, electricity, and magnetism. Newton's influence was so powerful that even centuries later, scientists still view mathematics as the essential tool for exploring nature. His framework shaped the scientific method, which emphasizes observation, hypothesis, mathematical modeling, and experimental verification. This method became the cornerstone of all modern science. Newton also destroyed the idea that nature is influenced by hidden, supernatural forces. People once believed that objects fell because they sought their natural place, or because Earth possessed a mystical attraction. Newton replaced these ideas with the concept of force, a measurable interaction that produces acceleration. Gravity became a mathematical relationship between masses, not an invisible preference. Motion became a consequence of forces, not a tendency of objects to move because they felt like it. This transition eliminated the need for mystical explanations. Nature no longer acted out of intention or purpose. It acted according to mathematical necessity. This change altered human psychology as much as it altered science. People began to trust reason over superstition. They began to question religious or mythical interpretations of natural events. They began to believe that the universe was understandable through human intellect. This shift laid the foundation for the Enlightenment, a period of intellectual growth fueled by rational thought and scientific inquiry. Newton became a symbol of the power of human reasoning. His success suggested that if humans applied logic and mathematics, they could uncover the laws behind everything, from mechanics to society. The idea that the universe is a lawful, orderly system encouraged people to pursue education, exploration, and invention. Newton's revelation also had profound philosophical implications. If the universe operates on mathematical laws, then every event has a cause, and every cause produces an effect. This deterministic view of nature shaped philosophy, politics, and economics. Thinkers began exploring whether human behavior, social systems, and economic forces were also governed by laws that could be discovered and applied. While modern science eventually moved beyond strict determinism, the idea that the world is lawful and understandable remains central to modern thinking. Another important element of Newton's transformation was the shift from a universe governed by perfection to one governed by mathematics. Ancient thinkers believed celestial bodies moved in perfect circles because circles were aesthetically pure. Newton showed that orbits obey mathematical laws based on gravity and inertia, resulting in ellipses rather than perfect circles. This insight replaced idealized geometric assumptions with mathematics grounded in physical reality. The universe was no longer an imagined perfection, but a measurable system governed by forces and motion. Newton's mathematical laws also replaced arbitrary rules with universal ones. Earlier theories often applied only to specific situations or assumed exceptions based on philosophical beliefs. Newton eliminated exceptions. His laws apply everywhere, on Earth, in space, in laboratories, in everyday objects, and in celestial systems. This universality allowed science to expand without constantly revising foundational principles. Newton created a stable framework upon which centuries of scientific discovery could be built. His equations became the backbone of classical mechanics, engineering, and astronomy. The predictability introduced by Newton also enabled long-term forecasting of natural events. Astronomers could predict eclipses centuries in advance. Engineers could calculate stress on bridges before construction. Artillery officers could compute projectile trajectories. Physics became not just a tool for understanding, but a tool for planning. Governments, military forces, navigators, and industries benefited from the ability to predict outcomes. This predictability gave humanity unprecedented control over the environment. Newton's revelation also shifted the understanding of randomness. Before him, events that seemed unpredictable were attributed to chance or divine intervention. After Newton, unpredictability was viewed as the result of insufficient data or complex interactions, not supernatural causes. This mindset encouraged scientists to gather more precise measurements, refine calculations, and improve instruments. The improvement of telescopes, clocks, and measuring devices was driven by the desire to align reality more closely with Newton's mathematical predictions. In addition to altering the external world, Newton changed the internal world of human thought. His idea that nature is governed by laws inspired generations of scientists to search for more laws, of electricity, magnetism, thermodynamics, chemistry, and biology. This process created the scientific disciplines we recognize today. Newton showed that if you look deeply enough, you will find patterns. This belief became a guiding principle of scientific investigation. Newton's revelation also changed the cultural identity of science. Before him, natural philosophers were scholars who debated ideas. After him, scientists became investigators who collected data, built models, and tested predictions. Newton transformed science from a speculative art into a quantitative, predictive discipline. He gave science a new identity based on rigor, logic, and mathematical structure. The transformation he inspired did not stop with his own discoveries. His methods encouraged others to explore the universe with mathematical precision. From Maxwell's equations of electromagnetism to Einstein's theory of relativity, every major advancement in physics builds upon the idea that nature follows mathematical laws. Newton introduced the template for modern scientific discovery. Even today, centuries later, Newton's influence remains visible. Whenever engineers calculate stress on a material, whenever physicists analyze a force, whenever astronomers chart the motion of planets, and whenever a student solves an equation in physics class, they are participating in the world Newton created. The belief that nature is lawful, predictable, and mathematical defines our culture, technology, and understanding of reality. Newton did not merely propose scientific laws. He revealed a universe governed by logic instead of mystery. He replaced arbitrary explanations with elegant equations. He replaced fear of the unknown with confidence in discovery. He replaced superstition with science. This revolution continues to shape modern life, from space exploration to digital technology. Every device, machine, and scientific model we use today embodies Newton's message that the universe follows mathematical laws, and those laws can be understood. The connection between Newton's laws and daily actions becomes even more astonishing when we examine the complex systems that rely on them. What seems ordinary on the surface, like opening a door, throwing a ball, tying a shoelace, or pouring water, is in fact a sophisticated dance of forces. These actions require precise balances of motion, friction, gravity, and reaction forces. We don't usually think about such details because our bodies intuitively perform these movements, but Newton's principles govern every single one of them behind the scenes. Part B continues by diving deeper into these hidden mechanics. The invisible physics behind simple movements. Consider something as small as tapping your finger on a table. This simple action illustrates the complexity of Newton's laws. When your brain sends a signal to your finger, muscles contract, generating internal forces. These forces accelerate the finger downward, second law, while inertia resists the change in motion, first law. When the finger makes contact with the table, the table pushes back with an equal force, third law, creating the tapping sensation. Even the vibrations that travel through the table and air as sound waves are consequences of forces transferring energy through materials. Something so trivial is, in reality, a coordinated sequence of Newtonian events. Walking is another example that appears effortless but actually showcases a brilliant harmony of forces. When you take a step forward, your foot pushes backward against the ground. This backward push is crucial. It creates friction, which enables the ground to push you forward with a reaction force equal and opposite to your push. Without friction, like on ice, walking becomes extremely difficult because the reaction force is too weak to propel you forward. Your body's movement is a constant negotiation between inertia keeping you from stopping suddenly, gravity keeping your feet on the ground, and muscle-generated forces changing your direction or speed. Every stride is a blend of Newton's laws interlocking perfectly in real time. Even the simple act of picking up an object relies on Newton's principles in multiple stages. First, your hand accelerates toward the object, overcoming inertia. Then your fingers exert a gripping force strong enough to overcome gravity pulling the object downward. The tighter you grip, the greater the force applied to resist slipping. When you lift the object, your upward force must exceed the object's weight. Once it's in your hand, inertia tries to keep it moving, so you must apply a controlled opposing force to stabilize it. Each component of that sequence, reach, grip, lift, stabilize, is governed by Newton's laws and would be impossible without them. The subtle role of friction in daily life friction is often overlooked, yet it is the unsung hero that makes Newton's laws functional in our everyday world. Without friction, most of our actions would be futile. When you turn a doorknob, friction between your hand and the knob allows you to apply torque. When you write with a pen, friction between the pen tip and paper deposits ink in a controlled path. Even sitting in a chair depends on friction between your body and the seat to prevent you from sliding off. Driving especially showcases the critical role of friction. Tires grip the road surface due to static friction, enabling acceleration, braking, and turning. Newton's second law tells us that acceleration requires force, but without friction, the tires would spin uselessly. When the car accelerates forward, tires push backward against the road surface. The road responds with an equal and opposite forward force that actually moves the car. This process perfectly illustrates Newton's third law operating through friction as the medium. Braking showcases Newton's first law. A moving car wants to continue moving at the same speed and direction due to inertia. When brakes apply force, they create friction between the brake pads and wheels, opposing the car's motion and reducing speed. The heavier the car, the more inertia it has, and the more force required to stop it. An everyday demonstration of Newton's second law as well. Turning is another fascinating example. A car cannot change direction unless a force acts sideways. When turning the steering wheel, the tires push sideways against the road, and the road pushes back sideways, creating centripetal force. Without sufficient friction, like on a wet or icy road, the sideways force becomes too weak to redirect the car's inertia, causing skidding. Every safe turn on the road is an invisible battle between inertia and friction, governed entirely by Newton's laws. The balance of forces in human movement, every action your body performs, is a sequence of force balances. Our skeleton and muscles operate like a highly complex system of levers, pivots, and pulleys, all obeying Newtonian mechanics. When you lift your arm, muscles attach to bones and pull across joints, producing rotational forces. These rotations follow Newton's laws just as linear motions do. Even standing still is not truly motionless. Gravity constantly pulls your body downward, and your muscles continually make tiny adjustments to apply equal upward forces to maintain balance. Your feet provide friction against the ground to prevent slipping. Your center of mass must stay aligned with your base of support. All these actions occur subconsciously, but they reveal an astonishing precision governed entirely by force interactions. Balance becomes even more Newtonian when you move. A person riding a bicycle, for example, stays upright by constantly shifting their center of mass and steering to counteract falling. Gravity tries to tip them over, inertia resists sudden changes in direction, and friction between the tires and road enables motion. Even the circular motion of the wheels involves centripetal force pulling the bicycle continuously toward its turning path. Cycling, therefore, is an ongoing dance of Newton's laws from start to finish. How tools, machines, and appliances rely on Newton, many objects we use daily operate on Newton's principles. A hammer uses inertia to deliver strong impacts. When swinging a hammer, you accelerate it with your muscles, and inertia keeps it moving until it hits a nail. The impact is then explained by Newton's third law. The hammer exerts force on the nail, and the nail exerts an equal force back on the hammer. A refrigerator door uses Newton's first law. When closed, the door stays shut due to magnetic force and inertia until an external force acts on it. When you pull on the handle, the door resists at first due to the magnetic seal and inertia, then swings open once you overcome those forces. Fans, mixers, and blenders function via rotational forces, which also follow Newtonian mechanics. When a fan spins, its blades push air backward, and air pushes the fan forward slightly in response, a third law pair. When you mix ingredients with a blender, inertia resists initially, causing a slight jerk. Once the motion becomes stable, continuous force keeps the blades spinning, a perfect demonstration of the second law linking force and acceleration. Elevators showcase a more dramatic interaction of forces. Gravity pulls the elevator downward. Cables and motors apply opposite forces to lift it. When stopping, inertia tries to keep the elevator moving, so brakes apply an opposing force. Passengers feel this as a slight jolt. During starts and stops, Newton's laws made tangible. Transportation, a masterclass in Newton's laws beyond cars. Nearly every mode of transportation reflects Newtonian mechanics. Airplanes fly because engines push air backward, and air pushes the airplane forward, Newton's third law again. Wings create lift by redirecting air downward. In reaction, the plane is pushed upward. Inertia keeps the plane cruising smoothly, while gravity continuously attempts to pull it down. Pilots manage these opposing forces at every moment. Trains, when locomotives pull long chains of cars, inertia becomes a critical factor. Starting the train requires enormous force to overcome the inertia of many connected cars. Once in motion, much less force is needed to maintain speed. Braking, however, requires long distances because the inertia is extremely large. A second law demonstration writ large. Boats move forward when propellers push water backward. Water responds with a forward reaction force. Waves, currents, and wind all exert forces on the boat, and maintaining motion requires continuous counteracting forces. In all these systems, Newton's laws are the foundation enabling movement, control, and stability. Sports as a showcase of pure Newtonian action, sports magnify Newton's laws dramatically. Every athlete uses force, motion, and reaction principles constantly. In soccer, kicking a ball applies a force proportional to the ball's acceleration. A heavier ball accelerates less for the same force, Newton's second law. When the ball hits a goalpost, the post pushes back with equal force, changing the ball's direction, Newton's third law. In basketball, players use force to launch themselves upward against gravity. When dribbling, the ball pushes the floor downward, and the floor pushes the ball upward. The speed of the dribble depends on how much force the player applies, inertia of the ball, and gravity pulling it back down. In cricket or baseball, hitting the ball illustrates an extreme third, law interaction. The bat exerts force on the ball, sending it flying, while the ball exerts force on the bat, causing vibration and recoil. Even swimming depends on Newton's third law. Swimmers push water backward, and water pushes them forward. Without this reaction force, swimming would be impossible. Sports, therefore, are highly visible demonstrations of Newton's laws in motion. Every kick, swing, jump, sprint, or throw is a perfect physics lesson. How Newton's laws shape safety and design everyday safety mechanisms are built entirely on Newtonian predictions. Seatbelts save lives by counteracting inertia. In a sudden stop, your body wants to continue forward, but the seatbelt applies a force that prevents that. Airbags distribute force over a longer period, reducing acceleration and the injury it might cause. An application of the second law. Helmets protect your head by absorbing force during impact, reducing the acceleration to your skull. Shock absorbers in vehicles, shoes, and machinery all reduce force transfer over time, minimizing damage by manipulating acceleration. Even architecture relies heavily on Newton's laws. Buildings must resist forces from wind, gravity, and earthquakes. Engineers calculate how much force materials can withstand and how structures respond to inertia during sudden movements. Every safety feature we rely on is rooted in the laws that govern motion and force. The hidden role of Newton's laws in communication and technology, even modern technology, phones, computers, satellite, depends indirectly on Newton's laws. When you tap your screen, your finger applies force. Mechanical systems, MEMS sensors detect that force by measuring tiny deflections governed by Newtonian motion principles. When a phone vibrates, a tiny motor rapidly accelerates and decelerates a weight. The reaction forces cause the device to shake. Satellites stay in orbit because inertia keeps them moving forward while gravity pulls them inward. This balance between inertia and gravity is a direct Newtonian relationship. Cameras use stabilization systems that counteract motion using equal and opposite forces. Everything from the internal mechanisms of hard drives to the balancing of drones in the air depends on Newton's principles. The unescapable truth: Newton's laws are always in control no matter what you do. Stand, sit, walk, lift, push, drive, or think, Newton's laws are at work. They govern the behavior of objects around you, the functioning of your body, the machines you use, and the vehicles you travel in. Even emotions like fear or excitement don't escape them. Your heartbeat accelerates and decelerates according to force inputs from muscles. The world is a constant conversation of forces, motions, interactions, and reactions. Newton's laws are not abstract ideas, but the very language the universe uses to operate. Everything is predictable, measurable, and interconnected through these fundamental principles. Understanding the shocking extent of Newton's influence transforms everyday life into a continual physics lesson. Every moment becomes richer with meaning because the hidden workings of reality become visible. Once you learn to see the forces behind the motion, you can never look at the world the same way again. When we say that Newton's laws transformed our understanding of motion and gravity, we mean far more than a scientific advancement. We mean a complete rewriting of how humanity interpreted the physical world. Before Isaac Newton, the universe seemed governed by mysterious forces, unpredictable behaviors, and philosophical assumptions more than measurable rules. People relied on incomplete ideas from ancient thinkers, observations mixed with assumptions, and explanations that were not based on mathematics or experiments. Newton changed all of that. His laws of motion and his universal law of gravitation provided a unified, mathematical, testable framework that described how everything moves, from a falling apple to distant planets orbiting the sun. That transformation reshaped science, technology, engineering, and the way humans perceive nature itself. To understand the significance of his transformation, imagine the world before Newton. For centuries, people believed in an Earth-centered universe, where the sun, planets, and stars revolved around us. Motion on Earth and motion in the heavens were treated as unrelated phenomena. The great philosopher Aristotle had declared that objects naturally sought their natural place, and that heavier objects fell faster than lighter ones. These ideas dominated the understanding of physics for nearly 2,000 years. Even when Galileo began questioning these assumptions, proposing that objects fall at the same rate regardless of weight, and that motion continues unless stopped, the world had not yet embraced a unified view of physical laws. No one had fully connected the dots between earthly motion and cosmic motion. No one had shown that the same principles govern a ball rolling on the ground and the moon moving in orbit. Then came Isaac Newton, a thinker whose insights stitched together the fragmentary observations of the time into a cohesive explanation that revolutionized science. Newton did not simply describe motion. He mathematically proved the relationships that govern it. He explained how forces cause acceleration, why objects resist changes in motion, and why every action produces an equal and opposite reaction. These were not philosophical claims, they were scientific laws that could be tested, predicted, and universally applied. And the most astonishing breakthrough was his proposal that gravity, previously thought to be an Earth-specific phenomenon, actually extended to the entire universe. The force that caused an apple to fall was the same force that controlled the motions of planets and moons. No one before Newton had made that connection in a way that could be mathematically demonstrated. This is why the statement Newton's laws transformed our understanding of motion and gravity is not an exaggeration. It represents a seismic shift in human knowledge. Newton replaced mystery with mathematical clarity. He replaced assumptions with experiments and logical reasoning. He replaced the belief in separate celestial and earthly physics with one unified theory under universal laws. His laws of motion and gravitation gave scientists the ability to predict and explain events with stunning accuracy. Suddenly, it became possible to calculate how far a cannonball would fly, how fast a planet moves around the sun, how tides behave, and how structures must be designed to remain stable under forces. This transformation moved humanity into the age of classical mechanics, the foundation upon which modern physics, engineering, and space exploration were later built. One of the most important ways Newton transformed our understanding was by establishing that motion is not something that requires a constant cause. Before him, many believed that objects moved only when acted upon continuously. If something stopped, people assumed it was because the force ran out. Newton clarified that motion continues unless an external force interferes. This concept, known as inertia, completely changed the way people understood why objects behave as they do. It revealed that the natural state of an object is not rest but constant motion in a straight line unless influenced by another force. This was a shocking shift from earlier beliefs, yet it elegantly explained countless everyday phenomena. Why a ball eventually stops rolling friction, why you lurch forward in a braking car, inertia, and why astronauts float in space, lack of external forces to slow them. Newton's second major transformation concerned the relationship between force and acceleration. Before Newton, force was a vague idea, loosely described and often misunderstood. Newton defined it with mathematical precision. The acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. This simple yet powerful idea allowed scientists to quantify movement. Suddenly, the world could be described in terms of equations. Engineers could calculate the strength needed to lift loads. Inventors could design machines with predictable outcomes. Physicists could explore the laws governing energy and momentum. Without Newton's second law, there would be no modern engineering, no understanding of thrust, no predictable motion of machinery, no analysis of structural stability, and no ability to design vehicles or spacecraft. Newton's third great contribution: every action produces an equal and opposite reaction, shattered old assumptions about interacting forces. This concept clarified why systems remain balanced, why movement occurs in pairs, why rockets can launch into space, and why humans can walk without slipping into the ground. It revealed that motion is a product of interaction, not a one-sided phenomenon. This deepened the understanding of physical equilibrium, collisions, propulsion, and mechanical motion. Newton's third law is the foundation of everything from airplane lift to automobile traction to athletic performance. Without it, modern science would be unable to explain momentum transfer, recoil, or structural load distribution. But the most revolutionary transformation came from Newton's law of universal gravitation. Gravity was understood in a vague, limited way before Newton. People observed that objects fell downward, but they did not know why. Some believed Earth had a natural pulling power, others that objects sought their natural position. No one had imagined that this same force extended throughout the cosmos. Newton stunned the world by proposing that every object in the universe attracts every other object with a force determined by their masses and the distance between them. This seemingly simple idea explained everything: why planets orbit the sun, why moons orbit planets, why tides occur, and why objects fall at the rate they do. Newton showed that the heavens and the earth were not governed by separate principles. They were linked by the same gravitational force. For the first time in history, humans understood that the cosmos operated under the same rules as everyday life. This idea was revolutionary. It united astronomy with physics, bringing together fields that had previously been seen as unrelated. Newton's work paved the way for future scientists like Einstein to explore the deeper nature of gravity. But without Newton's foundation, none of modern astrophysics would exist. The transformation did not stop with scientific theory. Newton's laws form the backbone of modern technology. Every car, airplane, rocket, machine, bridge, and building is designed using principles derived from Newtonian mechanics. Engineers rely on these laws to calculate loads, stresses, accelerations, and trajectories. Pilots rely on them to understand lift and drag. Astronauts rely on them to navigate space. Even the functioning of everyday tools like bicycles, elevators, and engines is rooted in Newton's insights. Without Newton, modern civilization, as we know it, simply would not exist. Another aspect of Newton's transformative impact is the shift from philosophical explanations to empirical science. Newton insisted on evidence, measurement, observation, and mathematical consistency. This approach helped establish the scientific method as a rigorous framework for understanding the world. Before Newton, knowledge was often accepted based on authority or tradition. After Newton, knowledge required proof. His influence extended beyond physics, into chemistry, engineering, mathematics, and even philosophy. His work inspired generations of scientists to question, test, and refine theories, ultimately leading to centuries of progress. Newton's laws also shaped the way humans perceive themselves in the universe. By demonstrating that the same forces governing falling apples govern the movement of planets, Newton challenged the belief that humans occupy a privileged, central position. He showed that the universe operates on universal laws, independent of human beliefs or observations. This democratization of physical principles helped fuel the Enlightenment, a period that emphasized reason, science, and intellectual exploration. Newton's influence extended into culture, education, and the collective mindset of humanity, encouraging people to trust logic and evidence rather than superstition or tradition. One of the most shocking aspects of Newton's transformation is how accurate his laws remain centuries later. Even today, engineers, architects, and physicists rely on Newtonian mechanics for most real-world applications. It was only when scientists began exploring extreme conditions, near the speed of light or within intense gravitational fields, that Einstein's theories expanded upon Newton's work. Yet even Einstein acknowledged that Newton's laws work perfectly for nearly all humans, Gale phenomena. This longevity and reliability reflect the depth of Newton's insight. His laws were not approximate guesses. They were fundamental truths about the nature of motion and gravity. Newton's work also opened the door for the Industrial Revolution. Machines, factories, steam engines, and technological innovations are all rooted in principles of force, motion, and energy. The ability to design and optimize mechanical systems relies entirely on understanding how forces act on objects. Newton's laws made this possible by providing the mathematical language needed to analyze and build complex systems. They allowed inventors to move from trial and error experimentation to predictable engineering. This shift was crucial for mass production, transportation, and modern infrastructure. The impact of Newton's transformation extends even further when considering space exploration. Rockets operate based on Newton's third law. Orbits are predicted using Newton's law of gravitation. Spacecraft trajectories are calculated with Newton's second law. Without Newton, humanity would never have reached the moon, sent satellites into orbit, or explored other planets. GPS, telecommunications, weather forecasting, and global connectivity all depend on Newtonian physics. Every satellite orbiting Earth follows calculations derived from Newton's gravitational equations. In this sense, Newton did not merely transform our understanding. He gave humanity the tools to leave Earth and explore the cosmos. Another reason Newton's transformation was so significant is that it introduced mathematical precision into the study of the natural world. While earlier thinkers made qualitative observations, Newton made quantitative predictions. His equations allowed scientists to calculate exact values for acceleration, force, and gravitational pull. This precision elevated physics to a mathematical science and ensured that predictions could be tested and verified. The reliability of Newton's formulas helped establish trust in scientific inquiry and set the stage for all modern experimentation and technological advancement. Perhaps one of the most transformative aspects of Newton's work is that it revealed the universe to be governed by consistent laws. This idea, which seems simple today, was groundbreaking at the time. It suggested that nature is not chaotic, but orderly and logical. It inspired the belief that by studying natural laws, humans could understand and eventually control aspects of their environment. This idea fueled centuries of scientific discovery, inspiring researchers to uncover new laws, develop new technologies, and push the boundaries of knowledge. Newton's laws also changed the way education developed. For centuries, physics education has been built around Newtonian mechanics. Students around the world learn about inertia, acceleration, force, momentum, and gravity using Newton's formulations. These concepts form the foundation of scientific literacy and are essential for understanding everything from mechanical systems to biological movement. Newton's influence reaches every classroom, shaping the minds of future engineers, scientists, and thinkers. The transformation brought by Newton's laws can also be understood in terms of their philosophical implications. Newton showed that the universe is deterministic. Given the initial conditions and the forces involved, the outcome can be predicted with precision. This idea influenced not only science, but also philosophy, leading thinkers to view the world as a predictable, governed system. It reshaped discussions about free will, causality, and the nature of reality. Newton's laws were not merely scientific. They were intellectual forces that changed how humanity conceptualized the universe. Furthermore, Newton's discovery that gravity acts universally introduced the idea that the universe is interconnected. Every object influences every other object through gravitational attraction. This concept helped pave the way for later theories in physics, such as relativity and cosmology, which explore even deeper levels of interconnectedness. Newton's laws thus served as the first step toward understanding the complex web of interactions that define the cosmos. In summary, the statement that Newton's laws transformed our understanding of motion and gravity captures not only the scientific revolution he initiated, but also the profound philosophical, technological, and cultural shifts that followed. Newton replaced confusion with clarity, replaced assumptions with mathematics, and replaced isolated observations with universal principles. His laws form the foundation of classical mechanics, guiding everything from the way we build machines to the way we explore space. The transformation he sparked is so deep and enduring that modern civilization still depends on it every day. Newton did not simply change science. He changed humanity's relationship with the universe, revealing that everything from a falling apple to a distant star is governed by the same elegant, unbreakable laws. The profound transformation brought about by Newton's laws becomes even clearer when we examine how his ideas reshaped every scientific discipline and every practical field touched by motion, force, or structure. Newton didn't simply provide a few laws. He provided an entire conceptual revolution that established a new way of thinking. Once he introduced the idea that nature follows precise, mathematical laws. Other scientists began applying this principle across chemistry, biology, astronomy, and even finance. Newton created an intellectual model that encouraged humans to seek patterns, measure phenomena, and trust the consistency of natural laws rather than rely on beliefs or assumptions. One of the most remarkable ripple effects of Newton's transformation was the explosion of scientific confidence it produced. Before Newton, many scholars believed that certain mysteries of nature, such as celestial motion, were beyond human comprehension. People felt that the heavens were governed by divine or supernatural order, inaccessible to human reasoning. By proving that the motion of planets could be explained through universal gravitation and the laws of motion, Newton demonstrated that even the grandest phenomena were governed by understandable, discoverable principles. This breakthrough inspired generations of scientists to ask deeper questions and pursue explanations for even more complex phenomena. Newton's achievement signaled that the universe was not chaotic or unknowable, but governed by elegant rules that humans could decipher. Newton's transformation also strengthened the relationship between mathematics and physics. Before him, mathematics and natural philosophy were often treated as separate fields. Although earlier thinkers like Galileo began integrating mathematical reasoning into physics, it was Newton who established mathematics as the essential language of physical laws. His formulation of calculus, developed to describe changing quantities like motion and acceleration, became one of the most important tools in scientific history. Using calculus, Newton described how an object's motion evolves over time under the influence of forces. This ability to mathematically model change allowed scientists to analyze much more complex systems than ever before. The unification of mathematics with physics created a powerful combination that would fuel centuries of scientific progress. A deeper examination of how Newton's laws altered the understanding of gravity reveals the magnitude of his contribution. Before Newton, gravity was seen as a simple downward pull limited to the Earth. Newton shattered this idea by proposing that gravity is universal, extending infinitely through space. Every object with mass exerts gravitational force on every other mass, no matter the distance. This radical idea redefined the structure of the universe. It explained why planets follow elliptical orbits, why comets move in long curves, and why moons remain bound to planets. Newton revealed that the universe is not a collection of isolated bodies, but a vast network of interactions governed by gravitational forces. This understanding allowed astronomers to predict celestial events with unprecedented accuracy. Eclipses, planetary alignments, comet trajectories, and orbital motions could now be calculated mathematically. This predictive power bolstered trust in scientific reasoning and made astronomy one of the most precise sciences. Newton's law of gravitation became the foundation for navigation, timekeeping, and mapping the world. Sailors used celestial mechanics to chart accurate routes across oceans, enabling global exploration and trade. Without Newton's work, the accuracy required for these endeavors would have been impossible. The transformation Newton created extended into the industrial world. Newton's laws became the foundation for mechanical engineering, which allowed humanity to design machines that could harness energy, lift loads, and automate labor. The Industrial Revolution, which began a century after Newton, was built almost entirely on Newtonian principles. Steam engines, textile machinery, water turbines, and mechanical tools all rely on predictable relationships between force, mass, motion, and energy. Engineers used Newton's laws to optimize efficiency, reduce friction, and improve mechanical performance. This shift powered enormous growth in manufacturing, transportation, construction, and agriculture. Newton's influence continued to spread as technology advanced. The development of automobiles, trains, airplanes, and ships all required deep understanding of Newton's laws. For example, designing an airplane depends on analyzing forces such as lift, weight, thrust, and drag, all rooted in Newton's laws. Aerodynamics emerged as a field that would not exist without the principles Newton introduced. Even sports science relies on Newtonian physics to analyze motion, improve athletic performance, and design equipment. When athletes throw, jump, kick, or accelerate, they are unknowingly applying Newton's principles. From baseball to basketball, every movement can be broken down into force, mass, acceleration, momentum, and reaction. Newton's law of gravitation also enabled humanity to develop accurate models of Earth's shape, size, and gravitational variations. These models were essential for creating maps, surveying land, and understanding geophysical processes. Without Newton, cartography and geodesy would have developed much more slowly, hindered by a lack of mathematical tools to describe gravitational forces and curvature. The ability to measure the Earth with precision laid the foundation for modern GPS technology, satellite communication, and global navigation. A powerful example of Newton's transformative influence is the field of orbital mechanics. When humanity first began exploring space, engineers relied entirely on Newton's laws to calculate launch trajectories, escape velocities, orbital paths, and re-entry angles. Every spacecraft launched into orbit must follow Newtonian principles. The speed required to break free of Earth's gravity was derived from Newton's equations. The timing and alignment needed to reach the Moon or Mars depend on Newtonian mechanics. Even gravitational slingshots, which allow spacecraft to gain speed by passing near planets, were predicted using Newtonian physics. She's not reach beyond P. Reality, she's trying to own you. Newton's transformation also revolutionized the understanding of tides. Before Newton, tides were poorly understood, often attributed to mystical or arbitrary causes. Newton demonstrated that tides result from the gravitational pull of the Moon and Sun acting on Earth's oceans. This discovery unified terrestrial and cosmic phenomena, showing that events on Earth are influenced by distant bodies. It also provided practical benefits. Sailors could predict tidal patterns, improving navigation and reducing maritime disasters. Today's tide tables, coastal planning, and marine science still rely on Newton's analysis. Newton's laws not only transformed physics, they transformed the way humans think about cause and effect. By establishing that every motion has a cause and every force produces a predictable outcome, Newton created a deterministic world view. This idea influenced philosophers, political theorists, psychologists, and economists. Thinkers began exploring whether everything, from human actions to economic systems, followed predictable rules. While later fields evolved beyond strict determinism, Newton's influence remains evident in the modern emphasis on data, prediction, and causal analysis. Another aspect of Newton's legacy is its impact on stability and structural engineering. Newton's laws explain how loads distribute through beams, pillars, and arches. Construction of skyscrapers, bridges, dams, and towers relies on calculating forces, moments, and stresses. Engineers evaluate whether a structure can withstand gravity, wind, earthquakes, and other forces using Newtonian mechanics. Without Newton's laws, humanity's ability to build safe, tall, or complex structures would be severely limited. Modern architecture stands on the foundation Newton laid in the 17th century. Newton's transformation even extends to everyday life in ways people rarely notice. When someone pushes a shopping cart, pedals a bicycle, lifts a weight, throws a ball, or opens a door, Newton's laws are at work. The resistance felt when pushing something heavy is inertia. The increase in speed when applying greater force is acceleration. The recoil from kicking a ball or firing a projectile is Newton's third law. The simple act of standing on the ground depends on the equal and opposite reaction force from the earth supporting your weight. These principles govern human movement as much as planetary motion. In medicine and biomechanics, Newton's laws are used to analyze movement disorders, design prosthetic limbs, study joint mechanics, and optimize rehabilitation exercises. Surgeons use Newtonian concepts to understand bone stress, tissue force, and muscle dynamics. Biomechanical engineers design artificial joints, supportive devices, and medical tools based on force analysis. Even X-ray imaging and radiation therapy involve motion and force calculations rooted in Newtonian physics. One of the often overlooked transformations Newton achieved is the distinction between weight and mass. Before Newton, these concepts were often confused. Newton clarified that mass is a measure of how much matter an object contains, while weight is the force of gravity acting on that mass. This distinction is essential for understanding gravity, motion, and energy. It explains why objects weigh less on the moon but have the same mass. This clarity paved the way for modern measurements and standards used worldwide. Newton's laws also laid the foundation for the conservation laws of physics, conservation of momentum, energy, and angular momentum. These laws are crucial for understanding collisions, rotations, and movement in isolated systems. Newton's work allowed physicists to analyze impacts, predict trajectories, and explore the dynamics of rotating bodies. Today, conservation laws are central to fields ranging from particle physics to mechanical engineering. Newton's transformation also shaped the methods used to teach science. His laws introduced a structured, rational world that helped educators develop clear instructional methods. Students learned to break down complex problems into fundamental principles, apply mathematical equations, and test hypotheses through experiments. This approach fostered critical thinking, problem solving, and analytical reasoning. The educational frameworks influenced by Newton continue to shape scientific training across the globe. Another aspect of Newton's impact is the shift from qualitative descriptions to quantitative models. Before Newton, descriptions of motion often relied on analogies or vague language. Newton replaced this with exact equations that could be tested and verified. This shift from words to numbers turned physics into a predictive science rather than a descriptive one. It allowed researchers to calculate outcomes before experiments were conducted, reducing uncertainty and accelerating progress. Newton's ideas also influenced art and culture. The Enlightenment movement, inspired partly by Newton's rational view of the universe, celebrated logic, clarity, and scientific discovery. Writers, artists, and philosophers embraced the idea that human reason could uncover the laws of nature. Newton became a symbol of intellectual power and scientific achievement. His work inspired literature, sculptures, and even political theory. The belief in a universe governed by laws influenced discussions about natural rights, political systems, and social order. The legacy of Newton's transformation continues even in modern theoretical physics. While Einstein's theory of relativity modified Newton's laws at high speeds and strong gravitational fields, it did not replace them for ordinary conditions. Newtonian mechanics remains accurate for the vast majority of real-world applications. Scientists still use Newton's equations to approximate complex systems, even when working with relativistic or quantum models. Newton's laws serve as the foundation upon which all later advancements are built. Additionally, Newton's influence extends into computational science. Simulations of fluids, projectiles, weather patterns, vehicle crashes, and mechanical systems rely on Newtonian physics. Video games, animation, and virtual reality environments all use Newton's laws to create realistic movements and interactions. Without Newton's transformation, modern digital worlds would be impossible to simulate convincingly. Newton's revolution in understanding motion and gravity also changed the trajectory of scientific inquiry. His ability to unite celestial and terrestrial physics set the stage for later discoveries that further deepened humanity's understanding of the universe. Einstein's work, quantum mechanics, and modern astrophysics all build upon the basic framework Newton established. Every major advancement in theoretical physics acknowledges Newton as its starting point. The final and perhaps most profound element of Newton's transformation is the shift in how humanity views itself in the cosmos. Newton showed that the universe is governed by laws that are accessible to human understanding. He revealed that humans are not passive observers, but capable of discovering and applying the principles of nature. This idea empowered societies to pursue technological, scientific, and intellectual advancement with unprecedented confidence. Newton did not just transform physics, he transformed human ambition. In closing, Newton's laws did far more than explain motion and gravity. They reshaped the entire foundation of science, technology, and human understanding. They transformed the world into a place where natural phenomena could be predicted, controlled, and harnessed. Newton's laws unified the heavens and the earth under one system, introduced mathematics as the language of science, empowered engineering and industry, and initiated centuries of unprecedented progress. The statement that Newton's laws transformed our understanding is not merely a recognition of scientific achievements. It is an acknowledgement of a turning point in human civilization. Newton revealed the structure behind the universe, and in doing so, he forever changed the way humanity thinks, builds, explores, and understands the world.